So let's start. Welcome to the deep dive of Prometheus. Some of you were here yesterday for the intro. Now we're going to go a little bit deeper. Same people as last time. And yeah, first half is Ben.
Oh, I'm doing the first half. All right. Back to the same questions. Who has heard of Prometheus? Yay! Who's considering using Prometheus? All right. So who's already using it as like a proof of concept or in testing? Few people. Good, good. And then who's shipped it all the way to production? Awesome. We're gonna have a lot of questions, aren't we?
Yep.
Back to Prometheus 101. It was inspired by Google's internal monitoring system. It's a numeric metric time series based metric system. It basically stores a series of numeric data points over time. It has a huge ecosystem of exporters and integrations. Hundreds and hundreds of applications implement Prometheus or have converters.
Than 300.
What's that?
More than 300.
Yeah, more than 300. It's a single tool for a single job. It's not a fix everything. It doesn't do tracing. It doesn't do logging. It's not an event store. It's just for the first level of monitoring. Our favorite plugin tool for Prometheus is Grafana. It's usually the second thing I install after I install a Prometheus server. The main selling points over other metrics-based monitoring systems is it's super highly dynamic, it's super efficient, we have a very powerful query language, and it's super simple to operate. A lot of people come to us and say, well, I don't want to host my own monitoring, it's a lot of work. You know, I've used Nagios, and we spend many engineers worth of time running Nagios or other older metric systems like Graphite. Prometheus is super easy to operate. It's not as big a deal as classic monitoring systems. Yes. Well, you want to say something about this?
I can do it. So now we are here at CloudNativeCon, and everything's in container, everything's a microservice, everything has sidecars, and all of a sudden you have this one thing, which is kind of a big thing in CNCF land, and it's one monolithic application, and this is Prometheus. And why are we doing this? Of course, normally you would just reasonably expect us to have like tons of small microservices and stuff, which then provide what we call Prometheus. But we're doing it exactly the other way around, for a very simple reason, and that is basically resilience.
Yeah.
Click. Yeah. Of course, what you really need for operations is, if you look at what you actually provide on the physical level and a little bit above, you need power and cooling for a data center. You need network connectivity to connect to your services and to debug and stuff. And you need observability, aka monitoring. And that's about it. The rest you can fix. So, because this is in the absolute critical path, we decided to have one single monolithic application, which is really easy to run, really easy to understand, really easy to deploy, and disregard all the cool bits and pieces on purpose.
Yep. Yeah. So one of the things that we discovered I used to be a site reliability engineer, and one of the things that we discovered that with complicated monitoring systems that depend on things like Cassandra or some other clustered database or any kind of monitoring system that depended on other components, those were the first things to fail whenever there was a small glitch in the network. And so we designed Prometheus to be a single standalone point that watches everything. And you can run multiple of them. And that way, if there's one Prometheus server on one side of your network and you have another Prometheus server on another side of your network, and there's a split brain or a partition, there's a recent outage that somebody, GitHub had, where they had a split brain in their network, and their clustering system just completely shit itself. And we don't have that problem with Prometheus because it doesn't have any external dependencies besides knowing where your targets are. And that's an extremely robust thing to do. where are we at now with Prometheus? So we have the storage backend. About a year ago, we developed a new storage time series database to significantly reduce the overhead of running Prometheus from a compute resource perspective. And also it significantly improved the performance of Prometheus when you're running Kubernetes clusters, where you're launching and creating and destroying pods continuously. So if you've got a CI pipeline, the old Prometheus had lots of problems with that. We also improved staleness handling. One of the old problems with Prometheus was as pods came and went, you'd still see the pod for 5 minutes until it would finally disappear. We fixed that. It's now much better. Yeah, we'll have links to the specifics of that at the end of the talk. And also, we've finally stabilized a remote read and write access to the database, so that you can take a Prometheus server and get access to the data or ship the data outside for more in-depth analysis or long-term storage. So Prometheus 1.0 had a bunch of problems. It had a single index for the entire lifespan of the Prometheus server, and this would grow and grow and grow as pods came and went, and that was a big problem. The original database was actually quite clever, but in terms of like how fast we could spin it up and get it going, but it turns out that creating a file for every single time series in a Kubernetes cluster just didn't scale. You know, we had at SoundCloud we had some CI pipelines that would rotate something like 500 pods 5 times a day, and so after a week we had like 50 million files on disk, and we actually overflowed the ext4 inode table. And so we had to reformat our Prometheus servers with more inodes. It was really annoying. And so that's what inspired the need to create a new time series database. And so yeah, the selection was also a little bit of a problem, because you had to go and read a whole bunch of different files. Yeah, so the new test setup to test the results of the new database. I don't know what we were going to say about that. You?
Okay. So basically, this is the test we did back then when we introduced the new storage engine for 2.0. We had one cluster with dedicated Prometheus nodes sitting aside of the cluster. And what we did is we had 800 microservices. We had 120K samples per second, 300K active time series, and every 10 minutes, 50% of those pods died and were put in anew. And this was the test setup. And the result was, drum roll, a 15 times reduction in memory usage, 6 times reduction in CPU usage, up to 100 times reduction in disk writes, 5 times reductions in on-disk size, 4 times reduction in query latency, and we actually can reproduce those results. If anyone doesn't trust us, of course, people tend to not trust us on these numbers, but they are actually really real numbers.
Yeah, we had one. We've had a couple of times where people have called us liars for how good Prometheus's time series database performance was, but then we showed that it was possible, and other time series databases like InfluxDB also were able to produce the similar results. One of the other things that we've introduced recently is as part of our code review pipeline, we actually built in PromBench so that we can automatically spin up using a GitHub / command to spin up a benchmark. So anytime we introduce a time series database change or an integration change, we can just spin up a whole Prometheus benchmark to see if we have a performance degradation, because every once in a while we make a change to the time series database, things get worse. So now we can basically spin up this benchmark anytime we want. Also with the remote ReadWrite API, this is much basically stable now. We have a whole bunch of integrations for external time series databases, and other related long-term storage methods. So if you have a very dynamic cluster, like you're running your Prometheus inside your Kubernetes cluster, you usually only want to keep a few days or maybe a couple of weeks of data inside the Kubernetes cluster, and you can use the remote write API to ship all that data out to an external storage for long term. So you still maintain the robustness where you can get your up-to-date data and your alerting done through that integrated Prometheus server, but for long-term dump truck data, you can use the external storage. Security and quality. We went through a security audit thanks to the Cloud Native Computing Foundation. We wanted them to focus on like making sure that we had a good data model and didn't have any really obvious security problems with Prometheus. The biggest thing that they came back and said is you really should have endpoint protection. So we are actually we took a vote at the last developer summit and said yes, we should probably start doing endpoint protection. So over the next some time, it's now on our to-do list to actually start implementing TLS encryption and authentication for exporter endpoints. So Prometheus has always supported encryption and authentication against targets, but we never promoted that as something that we should do in every exporter, because we just didn't have a big enough team to be able to handle the workload of supporting and maintaining security. And of course, there's a bunch of us in the Prometheus community that are security aware, and we didn't want to just implement something that looks like security, but actually makes you less, it doesn't make you any more secure, or makes it worse because we implemented bad security and you put your, you open it up to the internet and now you get owned because we implemented bad security. So we're going to implement good security, and it should make everybody happy. And then one of the things we changed recently after the developer summit was we are doing a much better job with the benchmarking and testing, and we're starting to do a better release cycle. So we're now doing every 6 weeks consistent release cycles.
No, you're jumping ahead.
Oh, am I jumping?
Yes. That is about stabilizing.
Oh, all right. Yeah, so of course, like happens when you create a new time series database, the first version had a bunch of bugs. So we spent quite a bit of time focusing on stability and fixing crash bugs and other stability problems with the time series database. So, and as you saw, 2.3.2 is the first version, which is actually considered really stable. So if you're using, if you're using anything older than this one, you should update, of course. That's the first one which we consider stable within the 2.x train. So as Ben already mentioned, we are having a new release process where we cut an RC every 6 weeks, and this 6 weeks is hard, so it doesn't take into account any time for the actual release or any beta testing or such. The RC is cut every 6 weeks. And basically once we are happy with that, and once it went through testing and people came back to us and said, okay, everything looks fine, then and only then we cut the release. No matter how long this takes, within that RC cycle, after 6 weeks, we start a new RC cycle. Also, if there's any really bad bugs, what we decided to do is we'll call a moratorium on any new features to re-stabilize. Of course, that's something we didn't do very well in 2.x, like maintain stability for end users. And we definitely needed to get better at that. So also there's quite some nice, and 2.4 and 2.5 are already under this new release cycle, which is why they're in this section. So Brian did something really nice. He made PromQL really, really quicker in a lot of cases. And this is already merged. It's, you might not notice this unless you have really large or complex queries, but still, there's a really, really nice change, especially in large deployments. Then also there's this recurring thing of long-term storage. So most people who, if they have to voice one concern with Prometheus, it's that they're not quite certain how to do long-term storage.
Myself, I just kept all my data, and my servers have data since the late 2015, so that works. Still, it's not the ideal working model. So as we fundamentally designed Prometheus to have distinct data islands, that's not something we're about to change within Prometheus itself, by definition and by design. But what we have is, we have our new storage, which allows you to actually take snapshots and backups, which wasn't possible with Prometheus 1.x. So that's already quite good if you need to restore something. And also this remote ReadWrite API allows you to export data to other things. And there's a ton of projects which integrate with our remote ReadWrite API. There's a total of 12 in the meantime. 2 which came from Prometheus itself are Cortex and Thanos. Cortex basically distributes the index and the ingesting on auto-scaling pods, while Thanos does a totally different thing, and it puts all the storage into object storage like Ceph or something, which is quite nice. And we actually expect those two to merge back again in some time, and then you have something like a distributed Prometheus, like a truly distributed Prometheus. But there's others as well, and we definitely do not want to say, okay, we endorse this one thing and you shouldn't use any other. Of course, we don't really want to be kingmakers. We want to see what the community comes up with, and whatever is best should just win. Of course, we don't have any profit motivation, so we can just do whatever and see what works best. Looking beyond just 2.5 and beyond, one thing which is still missing, we thought we would have that earlier, is like a proper ACID database. We have the atomacy, we have the consistency, we have the durability. We are still missing the isolation. There's a patch set which has been carried since early 2.x. It hasn't been merged yet, but basically what we're going to do to have proper isolation, as in you only get one full scrape in your data set, or you don't get it, but you never see a partial scrape result. That's what isolation means in this context. It's basically we just take a monolithic counter or monotonic counter, we count it up, and every ID or every scrape gets one ID, and unless that is committed, you don't return that sample, and no matter in which context. It's relatively easy, at least on this layer. But there's more beyond just Prometheus. Of course, if you know the story of Prometheus, how the Titans stole the light from the gods and gave it to the humans, there's quite some ambition in the name of Prometheus, and this is by design. So yes, we do actually want to change the world and actually change how the world does monitoring. We firmly believe that any hierarchical data structure in monitoring is doing it wrong by default. So labels, we consider labels one of the most powerful things which we have within Prometheus. And labels are encoded in our exposition format. So while there is a ton of political considerations about people supporting something called Prometheus exposition format, we actually want to push this system because that means people will start using labels more and more. So we came up with open metrics. Yeah, that's basically it. We are spinning out Prometheus exposition format. It's already a CNCF sandbox project. We are aiming to have an IETF RFC published, a full test suite, blah, blah, blah. So we have something actually official to run against. I'm currently actually writing the internet draft, which will hopefully become the RFC. And 2.5 already has open metric support, Prometheus 2.5. But it's experimental, it might change, it might break, we might do away with it, but it already works. And also our Python library already is able to emit 2.5, emit open metrics. So open metrics is just metrics. But what we can already do is we can attach exemplars in open metrics to certain histograms, to certain buckets. So basically you have a trace, and you know this ran for, let's say, more than 60 seconds, and then you attach one of those traces from that bucket of latency to your data. So you have a direct link between your latency bucket and your trace. And if you have really high latency, in some cases, you already know what trace ID to look at. There's some integrations like OpenCensus and StackDriver, for example, they want to have this, they want to support this, they want to ingest this data. Other are free. For example, Prometheus to just drop this reference to the exemplar. Of course, currently within Prometheus, we don't really have a use for it. This might change, it might not change, but so basically Open Metrics is designed to allow people to do this, but not force people to support this. And we're currently only looking at Open Metrics, but we also want to have more, because metrics is usually the start of your monitoring story or your observability story, but there's tons more to it. So we also want to have events, we want to have traces, we want to have all these things within something which looks like Open Metrics, where you have labels, where you have your well-defined data structures, basically to redo a new level of observability across the whole ecosystem. Tom Wilke is actually already working on something which is basically for like log files. If you imagine having Prometheus for log files, that's what he's working on, which is pretty awesome. And just by happenstance, it'll support Open Metrics or whatever we end up calling that other stuff. There's already quite a few people or companies who are committed to supporting Open Metrics. These are just the first adopters because there are in the meantime too many to list all of them. And yes, we do want to change the world, like seriously. We will always commit to having simple and resilient operation. That will always be the case. Our most important thing will always be to get from raw data through computation into alerts. Codestep is what enables you to keep your services up and running. We're talking to hardware vendors about emitting Prometheus and or Open Metrics data. Some of them are already working on that. And we always try to, it's a little bit in your face, but still we are also being serious about that one. We always want to be able to support 10x scale of today for tomorrow. Yeah, there's a few more talks. You can also download these slides from the schedule, so you can just look at them. And now we have time for questions.
Thanks for sharing. We use Prometheus in production, and I found sometimes we calculate the CPU usage right is not correct, because I found the root case is Prometheus collect the metrics with the timestamp is the script type, not the real timestamp. But if the kubelet has a delay matrix, and then Prometheus will correct the time data is not correct. That will cause the matrix is over the limit. So we try to find a solution. We fork a custom node exporter and implement the CPU usage right in the node exporter to override this shortcome. But I don't know whether it is the best practice or what's the opinion about the Prometheus calculation about the cumulative value in the future.
So you're collecting the CPU usage from the kubelet?
Yes, I collect the CPU usage from kubelet.
So there's a lot of indirection there, and actually the best thing to do is to have your Prometheus, instead of going through the kubelet, go directly to the node exporter, go directly to CAdvisor, and that way the timestamp for when Prometheus Connect collects the data from the target, it's getting it as direct as possible. And actually that's part of the design goal of Prometheus is we intentionally don't have a single server agent. We designed it so that Prometheus can talk to every metrics endpoint directly as quickly as possible with the least amount of delay and get the freshest data possible. And also part of our scalability design is that a single agent could take several seconds just to return the results of all the things on a server. Whereas if you create a granular set of metrics where you talk to your app and you talk to the kubelet and you talk to the CAdvisor and you talk to the node exporter, each of those happens in milliseconds. So it allows Prometheus to collect that data and really get it fine-grained and much more accurate.
We know that Prometheus only support float as its matrix type, right? And so I'm curious about what if I want to store a string as a matrix?
Okay, people want to store strings, so we store strings. So Prometheus does support strings. It's all in our index. So we have a pattern called an info metric, and what you do is you take your string and you make a label for it. So if you have something like there's Prometheus build info, contains the Go compiler version, the git commit of the server, and the actual Prometheus version string. And so all those strings are all as labels on a single metric, and the value of that metric is 1. And because of the Prometheus compression, storing 1 over and over and over again in a database seems like it might be a lot of overhead, but because of the Prometheus compression, that's only 20 bytes of storage for, what, every half an hour?
For 2 hours, I think.
Yeah. No, it's every 20 bytes for 120 samples. So if you're doing 15 seconds, it's half an hour. So you're only talking like a few hundred bytes to store that 1 over and over again for an entire day. So the overhead there is much smaller, and we store all those strings in our database. And so this actually leads to a bunch of really interesting use cases. For example, if instead of storing the kernel version, or the hardware version or the VM type as a label on every single metric, we put them into these info labels, and then you can use joins in PromQL to, if you want to correlate based on kernel version or VM type or hardware type or one of these other strings or versions. Like if you have 2 versions running in production, you can take and using a join and a group left, bring the version string of your app into your CPU metric for the app dynamically, and then now you can do correlation of CPU usage by version. And so this is an extremely powerful thing that you would usually do in like an SQL thing, but we can also support the same kind of thing in PromQL. And so the string handling, by having it be separate metrics, leads to some really powerful correlation possibilities. I actually did that once in production, where we had a JVM app, and some of the JVMs on the cluster were using 2 CPUs, and some of them were using 1 CPU. And it was the same binary, it was the same JVM, it was the same app, and they're all running. And we couldn't figure out why half the VMs or half the JVMs were using twice as much CPU. And so we started just using PromQL to correlate, like, well, what if it's the hardware type? So we had an info metric that had the CPU type, because we had some versions of these Xeon CPUs and we had some versions of these Xeon CPUs. No correlation. So I threw in and I did group left on kernel name. And so I brought the kernel name in, and boom, perfect correlation that the older kernel version made the JVM twice as slow. So well, guess what? We have to upgrade the kernel on all these servers. Just happens. So that's the power of PromQL.
More question? Yep.
Okay, thank you. So previously I used the Prometheus with remote storage. I saved it in FriendDB. So I found the performance is not a good thing. I'm using a Grafana to query the Prometheus, and the Grafana page is refreshed slowly. I'm not sure why. So this is the first question.
What specifically is refreshing slowly?
Sorry? What's the version?
What specifically is refreshing slowly? I didn't know.
I mean, if I use remote storage, I found the Prometheus query is slow. So.
So Prometheus is a very fast time series database, and many of the remote storage options are actually slower than Prometheus. And you're better off just using Prometheus instead of using remote storage, which is why, we're experimenting with many different remote storages. So whichever remote storage you're using, which one did you say you were using? Influx? I don't know that one.
Never heard of it.
It's official
We don't have an official suggestion.
So,
Yeah.
but if you want to have an unofficial suggestion, Cortex and or Thanos is probably your best bet.
Cortex and Thanos. Yeah, there's two different projects. Cortex is a Prometheus time series data, scalable time series database, and Thanos is a different kind of scalable time series database. So these are the two that I like the most. But yeah, many of the remote storage options are interesting, but are actually slower. Did you say timescale DB?
Yeah, this is the time scale.
Yeah, timescale DB is based on Postgres. So it's slow.
It's slow.
Another question. So I turn back to the local storage. So I think local storage is good and it can better performance. But it brings another question. So after several days, after 1 month, the disk is full. So I means I want to delete some of old data. Is it possible for the logos rotator?
You can tell Prometheus to persist for a maximum of time, and you also can tell Prometheus to only use that much storage, and it will start deleting all by itself. That's your best bet. There is also possibility to delete from the blocks, but this comes with performance penalties. So it's best to just cut off and just drop the data at the end. And basically you need to scale your storage in a way that if you let's say you want to have 2 weeks or 2 months of data, then you just need to do some calculations, maybe give some extra room, and that's your storage need. And everything which is older, you just drop. This is a command line flag for Prometheus.
Or attach a bigger volume.
Yeah.
And
Yeah.
I can set the parameter to storage how long.
Yes. Yeah. So you.
I change it, it will delete the old data.
Yes. So if you change the time, so because it's a command line flag, you stop Prometheus, you change the flag, you start it up again, and then it will garbage collect all the old data.
Yep.
I think we have time for one more.
Thanks, Benjamin. I've reviewed Cortex and Thanos, but I think all those projects are very complicated and brings great operation burden for us. So I'm wondering if Prometheus will plan to support local long-term durability and most importantly, on Prometheus downsampling, because if we have long-term durability storage, we have 1 year or 2 year data, we can't query them without downsampling. So I'm wondering if Prometheus 2 or 3 have plans.
So yeah, so we have discussed, so Thanos has downsampling, and it's really, really powerful. So it'll because it can do it in the background. We're currently working on the ability to do backfill, and once we have, what I mean by backfill is, if you have a Prometheus time series database, right now there's no way to just add more data to that without scraping right now. And what we're working on is the ability to add just take and bulk dump new data sets into a Prometheus server. And once we have that,
basically put it here.
Yeah, so if you have a bunch of data, we can just insert, actually not here, but we can just add a whole bunch of new time series as backfill. And the two reasons we want to do that first is one, so that we can do backfilled recording rules. So actually the best way to do downsampling right now is to do recording rules that create downsampled data. And then instead of querying the live data, because the Prometheus 2.0 time series database is totally durable all on its own. It's actually a really good, durable time series database, but it doesn't support mutation. It's a write once, and so using recording rules is a good way to do downsampling because you can set your query to query a bunch of data, and you can record it only once a minute. Because in Prometheus 2.0, we allowed per recording rule group intervals. So you could, if you wanted to create a once every 1 minute or every 5 minute, you can create those recording rules that only record every 5 minutes.
But if I do something this way, I have to set the retention time so long, and the high function data also remains
For a long time. Yeah, and it just takes up a lot of storage space. The other thing you can do is you can use federation is a simpler solution for on-prem. So you can create your recording rules and then use a federated endpoint and have one Prometheus server that's dedicated to long-term storage. And this is what RichiH does for his company. And also we do this for the same thing at GitLab. So we have the GitLab runner pool, and this is a huge auto-scaling group. And so it creates a lot of churn and a lot of data. And so we take and do pre-recorded data, and we pull that in.
Time's over.
Oh, time's up.
We will be heading down to meet the maintainers.
We're going.
Yeah, we will be heading down to meet the maintainers right now. So anyone who has questions, just follow us to the CNCF booth where we'll be staying for the next hour. And also 1500 to 1600 will be there again.